So just a reminder that we have quiz 3 tomorrow in section. And if you haven't let me know that you need to schedule something different, today's the day you need to let me know that. Otherwise, we'll expect you to see you tomorrow, bright-eyed and bushy-tailed, and ready to go. The Lab 5 checkoff is due tonight. Lab 6 is due next week. And if you haven't sort of internalized the new end-of-term schedule, please just look on the course website where we try to describe all that. So today we're going to sort of shift gears a little bit, and we've talk about sort of the techniques we use to glue all the components of a modern processing system together. And it's sort of interesting because those techniques have changed dramatically over the last 5 or 6 years, and we seem to be, headed in a new direction. But not to fear, a lot of the same basic questions that we used to talk about in terms of how to glue an entire sort of large physical system together. Now we're having to revisit all that to think about how to glue thousands of cores together within a single chip. So a lot of the interconnect issues I'll be talking about today are being revisited now in the context of these large multi-core machines. Okay. So when you think about all the components that go into a system, so we have different sort of hardware components like different memory systems and different storage devices and different CPUs, and then the operating systems and the sort of interfaces they provide. And you look at how all of these things play together to make an effective computer system. And you ask yourself, well, what's really, who's top dog? What's the most important thing? And the answer is it's the interfaces. Those are the things that actually survive the generations of technology changes. And so, in fact, the networking software that you're running is not very different from the networking software that ran on the machines of 20 years ago. The notion of doing IP and TCP and connecting to computers around the world, even though there's many orders of magnitude more computers to connect to, enough so that we were sort of running out of the 32-bit address space that was originally allocated for network addresses. The basic software is unchanged, even though we've gone from 1 gigabit chaos net to 10 gigabit Ethernet to 100 gigabit Ethernet to 1,000. We keep changing all the different technologies, and yet a lot of the systems remain unchanged. And so that's really a key part. And what we'd like to do is, as we think about the interfaces, that's really, in some sense, where the big investment should go, even though we tend not to. We tend to shrink wrap interfaces around whatever happened to be there at the moment. Say, aha, we'll just call that a standard and then we're done. It turns out that what we really want to do is to pay much more attention to sort of the right abstractions and think explicitly about how to survive technological change. So what we're going to do is in most modern standards are actually chosen to be sort of independent of particular implementations, which is great. And it should be pointed out that, for instance, the x86 instruction set, which has survived since its original implementation back in the original 8-bit 8088 microprocessor chip, is now a huge asset to Intel, because the world's software sort of has all been compiled down to x86 binaries, and the ability to continue to run those programs is of enormous use to Intel. I mean, that's why people why there's sort of only one processor architecture in the sort of desktop and laptop world. Similarly, in the mobile world, the ARM architecture has sort of gotten sort of the lion's share of that. It's a fairly energy efficient, space efficient instruction set. And more importantly, its rights weren't owned by Intel. And so a lot of people who wanted to escape the Wintel oligarchy went off and fell in love with an alternative. So these things have enormous consequences over the decades, and you'll probably be involved in at least experiencing, or depending on how you think about it, victimized by future choices about these interfaces. And you might want to think carefully about the choices that you make if you ever have a chance to do that. It's easy to identify lots of problems that can be created by simply going with whatever is expedient at the moment. I remember this was said in a different context about a particular software program, but the phrase has stuck with me ever since. David Moon, who was a staff member here, very sharp guy, was talking about a particular piece of technology, and he says, you know, a moment of convenience, a lifetime of regret. And that can sort of describe the sort of things that can go wrong when you make a bad choice. And in fact, a lot of the early PC architectures were really just based on the 8086 chip, and they turned out that was hugely limiting and probably prevented PCs from taking the world by storm. And it was really only after some of those problems that were solved that all of a sudden, you know, mainframes became the tail and PCs became the dog. So there's been many success stories, and one of the things we'll talk about today is some of the success stories that are oriented about how to communicate information from one part of the system to another, from one device to another. So in the old days, when we had a whole pile of things we needed to connect up, the CPU, the I/O system, the memory system, the disk, they just, you know, because it was all being sold to you in one big box and it cost $1 million and there wasn't really a commodity market in any sense. So all of these pieces of interconnect were custom designed around what they had to do, with really no thought of, well, in 10 years, are we going to be happy with this memory bus? The answer was, oh, who cares? In 10 years, we'll just re-engineer everything and it'll be what it needs to be. So our original machines, there wasn't really a notion of you know, sort of plugging other things into your computer other than what the manufacturer supplied to you. And a lot of the earlier angst came in some of the early systems when there were third-party vendors who were trying to sell memory systems for the 360 or the Digital Equipment Corporation machines. And there was a lot of, what the hell are you doing? That's our system. You can't plug your thing into it. But that was sort of the tip of the iceberg now, and pretty soon people came to expect that, in fact, systems should be inherently modular. I should be able to make my own choice for a video card or for a disk, independent of the choice I made for the CPU. I might have, you know, want to invest in much higher capacity I/O system than, you know, Intel was thinking about, and that should be okay. So the first thing that happened was we created sort of a modular interconnect system where everything was connected together by a single communications channel. And that communications channel really looked a lot like the pins on the CPU. So that communications channel consisted of, you could send an address, you could send data or receive data. There were some control signals which look remarkably like the control pins, you know, read and write, and MOE and write enables and the clock signals, all of which look suspiciously like the pins on the CPU chip. But it sort of got the job where now you would actually buy a different video card. And, you know, depending on whether you wanted high-end video or just simple character-only video, you could make some choices here and expect to plug those cards in to the computer system that you had bought. So there was this notion of sort of user expansion. And then we got on to these processor-independent buses, because it became pretty clear that there were some choices that individual CPU chips were making that weren't long-lived. They weren't forward-looking. They didn't take into account the ability of a very smart network interface transferring information all by itself into buffers in memory without any intervention from the CPU at all. And so we became from the notion where the CPU was really in charge and these guys were all slaves to a much more symmetric idea where each one of these guys could in fact become a master of the communication channel and communicate to whichever other peripherals they wanted. And one of the most important side effects of that is you could suddenly have more than one CPU involved in a system, and that was pretty neat. Nowadays, we're getting back to the old picture because, as it turned out, that as technologies got faster and faster and faster, these single communication channels, these so-called bus-based systems, are fine when you have many tens of nanoseconds in which to access memory or to send a message to the disk drive or something like that. But as processors became faster, tens of nanoseconds suddenly turned into tens and hundreds of instructions. And it became less plausible to sort of shackle the CPU to this ball and chain of a very slow common communication system. We'll talk a little bit about some of the intrinsic reasons why these single communication channels are slow. But the system engineers quickly came up. We started engineering, again, a huge sort of universe of interconnect, each tailored to a specific idea, a specific thing. You know, some of the interconnect was designed explicitly for plugging in external devices like USB. Other was specifically designed for very high throughput, reasonably low latency connections to these, to your memory system. And there was really no reason to saddle the memory system with some of the same constraints of, well, you better be able to have it, communicate across 7 feet of cable. And the CPU designer said, no way is our memory system going to be across 70 feet of cable. That would make it too slow by far. So they started getting back into the business of designing these special buses. And we'll talk more about where we've ended up in that transition. And then just in case the cartoon on the front of the lecture didn't make any sense, so these buses and there was an era in which there was a lot of talk about front side bus and back side bus, and hence you can look at the front page of the lecture and go, the typical feeble 004 joke. Okay, so, and there's some question about where we're going, although I think that has become clearer and clearer in the last couple of years, and I'll say more about that. So what's the big deal? I mean, what's magic about buses? They just seem like bigger logic circuits with, wires measured in many inches or maybe feet. Can't we just live with that? And the answer is no, but we take a little getting to that conclusion. So the first thing you say, look, come on, wires are the abstract notion of a wire is this equipotential way of electrical node where basically it has the same voltage everywhere all the time, at the same instant everywhere along the wire. And that's an abstraction which works well sort of locally. It works less well when we start thinking about long wires and fast transitions of voltages on wires and things like that. So, but at least in the abstract, we don't worry about time. One of the advantages of abstracting out, of having this abstract notion of wire is that we say, look, we're not, the time that it takes to transmit information physically from one end of the wire to the other at one point in the technologies was very, very fast compared to the speed of the actual logic gate, so it was essentially negligible. The transition that's happened is no longer negligible, and in fact, it may in fact represent the lion's share of the timing budget now. The logic gates operate in a couple picoseconds. Transmitting the information over a 1-inch wire takes many times that time. So it's sort of been interesting to watch how the generations of technology have turned on the head what was important. So this abstraction turns out, which was fine in the original computer architectures, turns out to have had to have been replaced by a much thorough understanding of how interconnect actually works. And how, in fact, every time you transmit a signal, there's actually a lot of interesting E&M that happens, electricity and magnetism that happens, and you actually have to understand that in order to have the transmission happen in as shortest time as possible. The notion that we're dealing in time spans where even passing information over an inch is huge. We don't have enough time in our time budget to allow for a 1-inch transmission at the speed of light. So, and we could say, oh, well, just forget about it. But if we did, our processors wouldn't run at 2 gigahertz or 3 gigahertz or 4 gigahertz. They'd run at these sort of, the abstraction didn't give us enough information. This nice abstraction didn't give us enough insight into what was happening for us to engineer things, to take advantage of everything we could in terms of speed. So in the abstract, you think about, you can think of, here we're transmitting information. If we're just simply moving information, in time, we're sort of just thinking about storage. And in the nice abstract way, we could think about communication really as simply moving information from one place to the other. And it would be nice if those two axes were sort of independent. But the point I'm trying to make in today's lecture, and something that will affect the engineering greatly, is in fact we can't move information across space without also considering that it takes time to do so. So that's really, we have all these sort of low-level things where you're saying, oh my goodness, you mean Maxwell's equations really matter? And the answer is, sadly, yes. We've reached an era in which the speeds that we're dealing with, they do matter. The fact that light only travels so far in a nanosecond or a picosecond is now a limiting factor for us. We do know that even though our devices are small, if I put 1 billion of them on a chip, it's going to take centimeters to do that. Our chips actually take real space, and then the transmitting information across the chip turns out to be a multi-cycle thing. It doesn't happen in a single clock cycle anymore. And finally, you could say, well, what makes things slow anyway, or fast anyway? And the answer is, well, we're charging and discharging these nodes. We're using these voltage-based representations of information. And simply charging and discharging capacitances through these switches takes time. And, the way information gets propagated along wires takes time. And you begin to see that now, because some of the interconnect on chips is turning to be optical, which is sort of odd, right? I mean, the idea that there's these tiny microscopic lasers shining at the other end of the chip in order to get information across the chip faster than it could get if you just tried to put it on a piece of copper wire. That's sort of remarkable, but that's what's happening now. Okay, so the real truth about wires. This sounds like the name of, I doubt that it will become a Hollywood hit, but it sounds like it, okay. Expose. The Republican senators will want to hold a hearing. Okay, can't we just legislate fast wires? And so, the answer sort of is, well, we developed an abstraction where we sort of bundled all the delay, the intrinsic delay of the gate, plus the delay of putting information out and charging and discharging all that capacitance, into one timing number. And that was a convenient abstraction that made it easy to think about the timing of a circuit. But the truth of the matter is that if I have a heavily loaded signal, here's some select signals, the select signal, which is actually visiting 32 2-to-1 muxes, right? So this is all 32-bit buses. So I have 32 copies of these 2-to-1 muxes, each of which is dealing with 1 bit of this 32-bit mux. And we begin to realize that there's a lot of loading on that select signal. It's suddenly going to 32 different logic gates. And that signal will be a lot slower than if it only went to a single logic gate. So this notion that we actually have to think about the loading, and that a better timing model, conceptually not as clean and as elegant, but would allow us to do a bunch of engineering that we can't do otherwise. A better timing model is to say, look, I'm going to think of the gate as having an intrinsic delay. How fast would it be if it had no loads on it at all? If I just looked at the output, it didn't go anywhere. And then I'll separately account for how many things I'm hooking to it. So if I go from hooking 16 things to it to hooking 32 things to it, right, I would expect in some ways some component of my timing to now be twice as slow, because there's now twice as much capacitance to charge and discharge. And so somewhere along the line, our timing model should probably take that into account. So what we'll do is when you start working on the design project, you'll notice this happening in spades in your beta, that there are things that will take hundreds of picoseconds, signals that will take hundreds of picoseconds to change, even though the logic gates themselves are operating in tens of picoseconds, right? And you could say, woo, it turns out that if I'm a bit careful about how I, instead of having one signal go everywhere, suppose I made 5 copies of the signal and have them each go to 1/5 the number of places, that'll turn out to make your beta noticeably faster. In fact, you can make almost a factor of 2 difference in the clock speed of your beta by taking into account these issues about loading and carefully distributing signals such that no one signal has to do all the work. Okay, so it's actually an interesting thing to suddenly peek under an abstraction and is and I think people are always doing this, is I have this great abstraction that's worked well for years, but if I look inside, is there an opportunity to do something better that used not to be possible because the technology has changed? And would that cause me to think a little bit differently about the abstractions I chose, particularly if I'm interested about power or performance? Okay, so one of the big issues is how do I communicate things, across something the size of a laptop? Right? I mean, I was just moaning about communicating across a chip, but your laptop is, 10 inches wide, or your desktop is, is a big box. Getting information around that system requires sort of a rethink from sort of the old days to the new days. So the old days, and this was a very elegant system, was we just basically had long copper wires. They were several feet long, and so typically, we'd have a 19-inch wide rack, so there'd be this 18-inch wide, PC board that had, stripes of wires running across it, and we would use those to transmit information in parallel from one card to another that we'd all plug into the backplane. So that would be a very simple way of getting expandability. And, we'd have information, we'd distribute power that way, so each card, some of the traces of the backplane, big fat ones, would be devoted to getting the, 5-volt power supply to each of the cards I would plug in. I would have a common clock, so there would be, I forever stuck with the image of the big sweaty guy and the old, the old galleys, pounding out this big drum, and all the rowers having to sort of go along with the beat of the drummer. And so we have this clock that I guess is a small sweaty chip that produces. And everybody uses that as the basic heartbeat for how to communicate information from one place to another in the system. So that's the way these things were organized. And in fact, if you have tens of nanoseconds, it's still a very convenient way because it turns out to be it's a simple, understandable communication mechanism, and it's low cost in the terms of electronics. Okay, and so to give you a sense of how that might work, here's the sweaty drummer here, and we're going to use both edges of the clock. We have one edge in which the sender changes what they're doing, and another edge that's called the assertion edge. So at the rising edge of the clock, whoever is trying to send information of bus puts new information that cycle for that clock cycle onto all of these parallel wires. And so that might include a signal saying, I want to start a transaction. It might include some information about the type of transaction, or read or a write. What address am I trying to get to? And in the case of something like a write, maybe it's, I'll give you some write data. In the case of a read, I'd be waiting for the slave that was addressed by this transaction to drive the data lines. The slave, on the other hand, waits for a while, and at the falling edge of the clock would basically look at the signals to decide what to do. And so the slave basically looks at the signals at the falling edge and says, aha. And so how do we choose the time between the assertion edge and the sample edge? Well, that time was chosen to take into account all the sort of vagaries of what it takes to transmit information down these, multi-inch wires. All the sort of complications having to do with, reflections off of impedance mismatches and just time of flight on the wire. And we want everybody to see the same information, but they don't all get it at the same time. Right? So this was just sort of a systematic way of saying, look, I'm going to give, 37 nanoseconds for the information to get everywhere in the system, and then everybody will look at it at the same time. And a lot of work, by the way, went into making sure that the clock edge arrived everywhere at the same time, which is sort of a separate engineering issue. And finally, there was with these sort of protocols where one component is communicating to another component. You have to take into effect what happens when, say, the addressed component has failed or isn't there. And so there was sort of a third participant in transactions, which was the bus itself, which would notice when a master had started a transaction for which there was no respondent. And the system would eventually say, oh, you don't seem to be getting an answer, so I guess I'll answer and say, you didn't, error. So that would be one way in which the CPU could distinguish, the master could distinguish between a transaction that was taking a long time from a transaction that had failed because of a missing thing. So the bus sometimes had its own role to play, a little bit of its own logic. So this worked pretty well in an era in which the bus transactions could be 100 nanoseconds or 50 nanoseconds. It didn't work much. A 10 megahertz transmission or maybe a 20 megahertz transmission, it didn't work very well after that, simply because it took too long for for the signals to propagate down these buses. And there's a bunch of issues. One is that there's the physical propagation time. The second is all the connectors on these buses introduce these small impedance changes in the bus. And if you take enough E&M, you begin to realize that the propagation of a voltage, I changed the voltage from 0 to 1, so I'm changing the electric field. The propagation of that change in electric field down this conductor depends crucially on the impedance of the conductor, how fast that goes. And more critically, if there's a change in the impedance, a little bit of the energy of that transition actually reflects off of that and starts traveling, making its own journey around the bus. And so not only are there these sort of echoes off the end because of the energy would get to the end of the wire and say, oh, I have nowhere to go. I'm going to bounce off the end. It gets reflected and it comes back. So these sort of echoes are sort of like yelling into a big canyon. It takes a long time for the information to get all the way across the canyon wall, and sadly it comes back at you later on. I'll say more about that in a second. Meanwhile, we have these bus systems which work fine, but then began to be have problems as things got faster. At the same time, I shouldn't say alternatively, at the same time, there was a whole new technology that explicitly dealt with distance communication, transmitting information over a long distance, where all the assumptions that were okay for a bus-based system but then began breaking down never held in the first place, transmitting information throughout a whole building. So this notion of how to create a network, which in some level has the same job as the bus, started dealing with these issues of transmitting information reliably over distances to many participants. It took that sort of as one of the things it had to solve from the get-go rather than just discover it 10 years in. And so there's this notion of sort of being inspired by how radio transmissions work and doing the same thing but confining the transmission not to the ether but to a wire so that we could, in a sense, the trouble is if we broadcast it, first of all, that's a whole separate set of technologies that we have to, the transmission technologies, antennas and things like that we have to worry about. But we run out of bandwidth. In other words, there's only, the ether only has so many, gigahertz, terahertz, or whatever it is, so many hertz of bandwidth. And if we had, we'd use it all up. The advantage of wires is we can build as much bandwidth as we want. If we just yell on the wire, if you want to make, yell to your friend, you can just have a separate wire between you, and our communications don't have to worry about sharing some, globally, shared medium. So this was a really neat idea. So we had cables that replaced the transmissions, but the basic idea was the same. And the whole notion of breaking information into packets and transmitting it in little chunks so that we could sort of verify the arrival of each chunk separately. And if a chunk went missing or went bad, we could just send that little chunk. From the get-go, it was built in that these communications had some unreliability. And the whole architecture of the communication system, both at the hardware level and at the software level, was carefully designed to account for these failures, right? It was also designed to accommodate technological change. So the notion of building a network that could run equally well on an IBM token ring or one of these Ethernet things that were just coming out in the 70s. People began to say, look, I want to be flexible. I want to use the best network that's available to me. There's actually many networks out there, so I want to start building my software stacks. And they thought carefully about what the levels of abstraction were. And in fact, if you take 602, this is discussed a lot. But the sort of modularity, both in terms of thinking about failure in the basic system, but building a system that can be expanded with more and more customers, and then reflecting necessary modularity in the software to sort of insulate yourself from technological change. That was all pretty insightful. And in fact, the system architects who were building the big CPU boxes should have done the same thinking. But so what were some of the lessons that we learned? And in fact, we'll apply those to the CPU interconnect in a slide or two. Well, one was that if you do voltage steps on a wire, you'll discover that if you don't worry about these impedance discontinuities, your signals, to use the technical term, turn to shit. Okay. So here's a nice signal, that the way you sort of thought it would look like when you designed your electronics. So here's a guy trying to put these pulses on the wire. Here's what it looks like if you pay no attention to the fact that you just run the wire, you listen to it somewhere in the middle, you don't worry about what happens at the end, the wire just stops. And all the energy of the transmission reflects off the end, and you get these horrible looking signals where all this is happening because of the reflection of this pulse off the end of the wire. And in fact, when it reflects, it inverts. And so we got these big upward going pulses, which are basically the echoes of the downward going pulse. So imagine if you had to communicate across a big canyon and it was echoing all the time. What would happen is soon that your voice, your message of 3 words ago would suddenly interact with the message, the thing you're trying to yell at the second as the echoes come back. That's exactly the problem that was here. And people began to realize that if I'm transmitting information across a certain distance, and I'll say what that certain distance is, I actually have to worry about these things. When things were slow, this never was an issue. Wires seemed very equipotential. When things got fast, and in fact, if I'm trying to make the voltage change, say, in 10 picoseconds from 0 to 1 volt, okay, if I have a wire that's longer than the distance light travels in 1 picosecond, then termination turns out to be, the wire is no longer equipotential. Okay, we have all these sort of impedance problems we have to worry about. And nowadays, people put every line on your PC board is an impedance-controlled trace. There's special electronics that deal with terminating it correctly, and that's essential to basically get very, very high-speed communication. And believe it or not, you have all the little communications channels that are actually connecting together the components on your chip are running at certainly, 5 or 6 gigahertz for sure, but on modern systems maybe up to 10 gigahertz. These are very high-speed transmissions that are happening. Okay. Well, just think for a moment. If I were actually going to say, okay, I buy the religion, Chris, how should I organize this? Well, the best thing I can do is to use differential mode signaling, okay, where I actually use 2 wires, and the receiver receives by measuring the difference in the voltage between the 2 wires. And that's as compared to a single-ended signaling, where I only use 1 wire. So why are 2 wires better than 1? What is going on there that would cause you to say, as an engineer, somebody who carefully took 802 and knows something about E&M, why would you prefer 2 wires than 1? I heard a voice, but it wasn't quite loud enough for me to... Yeah?
Any radio noise or electromagnetic noise will happen to both wires?
Right, so the advantage of this so-called differential signaling is that you get a very good, what's called common mode rejection. Something that would affect a single wire will in fact affect both wires pretty much the same. And in fact, you tend to engineer this so that anything that's happening happens to both wires. So you do twisted pair, or you do something fancy with a PC trace to make sure, they experience sort of this, they sample the surrounding noise in pretty much the same way. And the advantage of that is I don't care what happens to the wires as, together, because I'm only listening to the difference between them. So we have this notion of differential signaling as solving a whole class of problems that single-ended signaling doesn't. So that's a huge step forward. The other thing that's nice about this, if you think about if we're putting current in one wire to charge it up, we're taking current out of the other wire to discharge it. So in fact, in some sense, the same amount of current is flowing, right? We're just determining where it's going. Whereas down here, as we turn currents on and off, there's actually switching noise associated with the turning, going from connecting to one power supply to the other. Whereas here that we're drawing pretty much a constant amount of current and just deciding which wire it goes into. Down here, we're turning it on and off. And turning it on and off creates its own noise problems. The traditional backplane, where the wire is passive, this is very slow, okay? Think about the impedance that I see driving into this thing. So I have a characteristics impedance of the wire. Well, I see sort of in the middle, I see that going off on both sides. And in fact, that halves the effective impedance at this driver here. Which is to say that you carefully designed a 50 ohm trace and a 50 ohm driver, but when you start driving the 50 ohm trace in the middle, you suddenly see 25 ohm characteristic impedance, and now the driver's sort of going, whoa, I can't put enough current in the wire to do the right thing. So all your voltage steps are half of what you think they're going to be, and the whole thing, it turns out this was just problematic from the start, and the more people understood about the E&M, the more they realized the problems. And then if I switch from this driver driving to that driver driving, in the clean world, you can say, well, what difference does it make? He was putting on a 0, now this guy is putting on a 0. But it turned out there were big glitches as the current was being sourced and sunk, are those words, in different places. So lots of interesting electrical problems. Another thing had to do with how to, when I send you information, you have to figure out when to listen. When do I get the value off the wire? And I had this scheme that involved a single clock arriving everywhere at the same moment, so everybody saw the same thing. It turned out it was much better to encode the clock information, in other words, when to listen, when to get the value off a wire, okay, in the transmission itself. So it didn't matter where you were, your timing of when to look at the wire was relative to what's on the wire as you see it, not by, how anybody else sees it. So as you see, this is sort of a slide from 602, which I remember drawing. The idea is that every time there's a transition, well, that sort of tells you where some of the clock edges were, because the transmitter was using its own clock to figure out when to change values, 0, 1, 1, 0, so forth and so on. So you can infer where some of the clocks were every time there's a transition. And then knowing something about the nominal clock period, you could then infer, okay, when all the other clock edges happened. It turned out there was not a transition here because we were transmitting 1 in both cells. But I can, so long I have enough transitions, and in fact, we come up with these careful encodings, like the 8B, 10B encoding that you learned about in 602, or will learn about in 602, that guarantees enough transitions that this clock inference mechanism works correctly. And in fact, there's electronics at all these communication links now that are doing this sort of clock inference. And then we carefully choose to take the value out of the middle of the clock cycle to avoid any effects at of the changing of the signal. And this allows us to achieve quite high communication systems without having to include a separate wire for the clock, or in fact having to take into account skew at all. Each of you is making your own determination about when to sample the signal based on the signal that you're looking at. Okay, so we have this Ethernet technology, which used to have one wire, and everybody had to sort of share that medium. And there were some issues about if you're transmitting, when do I transmit? Again, in 602, you learned about the Aloha network, all these strategies for not trying to all broadcast at the same time and ruining everybody else's transmissions. So we had this sort of evolution of these point-to-point communication systems. So now modern Ethernets are not one big cable that goes to every drop in the building, but instead we have nothing but point-to-point communications and active electronics that takes packets from one wire, buffers it up, and then puts it on another wire. So nowadays, everything is sort of point-to-point. And in fact, in modern systems, pretty much single driver, single receiver, point-to-point communications is how everything works. It's how you communicate to your disk, it's how you communicate to your graphics card, it's how you communicate with your memory system, it's how you do pretty much all communication are these highly engineered, very high-speed, point-to-point communication systems. Okay. So we used to have these buses. Now we basically have nothing but these unidirectional serial point-to-point links. This is what PCIe is, and that's the primary interconnect in your computer these days. A single differential pair going one way and coming back, so sort of symmetrical communication. If you want, and we have individual clock recovery on in each direction and stuff like that. So it's this big high-speed serial, and as I say, these are running now at multiple gigahertz. So it's these tiny little 10 gigabit networks over these single wires from one of your chips to the chip next door. We want more bandwidth than we can get over that, although that's sufficient for most things. Things like video, it trivially fits into such a one-wire communication scheme. But if we want really, really high bandwidth, we can gang them up. We can use them in parallel. And you see that now. So you have graphics cards that use 8, it says PCIe times 8 or times 16. What that's telling you is it's using 16 of these channels in parallel. And it takes the big message, breaks it up into 16 little messages, transmit them over these 16 little networks. And then there's big electronics that assembles it all at the far end. It sounds complicated. It is. There's a lot of mechanism that goes into that. And it takes a lot of transistors to do that. Happily, transistors we got lots of. Okay, so in today's computers, everywhere you look, there are these very high speed. So this is a modern diagram of a system that you could have bought probably last year, but it's all about these very high speed point-to-point links. Okay, so Sauron would be happy. There's one thing that we use these days to connect up all the parts of the CPU. And away we go. Okay, this is just a little bit of detail about some of the numbers that are associated with the actual signaling across the PCI Express. Notice that there's several layers of packetizing that happen. Right, we start with our original message down here, which you might want to say, "This is a memory address, Mr. Memory System. Please, return that to me," or "Please, Mr. Graphics Card, draw a line from here to there." That's packetized and broken up into a whole sequence of packets, and so we have a sequence number for the packet. This whole thing is protected by a CRC, so we can tell if the payload has been corrupted. We then stick basically a synchronizing sequence at the stop and the end, so the low-level electronics can synchronize up the clock recovery and figure out when a packet starts. So, and this is all covered in 602, probably more than you wanted to know. So. Let's spend the last couple of minutes think a little bit about communication more abstractly. And this is where part of the most interesting sort of research is happening these days. So I spent the first part of the lecture pissing on buses, right? But they're very good because they're actually fairly inexpensive. And conceptually, if they're sort of reasonably short, or if you have the time to spend, I can communicate, anybody can communicate with anybody else, quote, in one step. It's a slow step, but if I have the time to have this sort of slow step, the time for information to get anywhere in the system, the bus is a very economical way to do it. The hardware cost is low. A variant on the bus, which uses nothing but point-to-point links, is a ring. Okay, and in fact, a lot of the early multi-core machines used a simple sort of ring to sort of collect information from all the processors and send it around, because it has the engineering advantage of being made up of think of this as a segmented bus, where each segment of the bus, there's somebody who takes the information from the previous segment and says, "I'll just reclock that data, get rid of any noise, put it out, and it's only going to go from me to you." So it's all point to point. So rings are nice. They solve some of the electrical difficulties here. They still have it still takes a little longer to get all the way around. But if it's really about sort of messaging from one, to neighbors, rings are very good. And in fact, all the neighbors can communicate with each other at the same time. Whereas here, only one communication can happen at once. So rings are a communication topology, which are very effective for a whole class of communications. Moving up a level, we can talk about costs that are sort of go now as the it's the number of nodes, right? We can have here we have a complete graph, so all the nodes can choose to communicate to each other at any given time. The hardware is quite expensive because notice each node is pretty much prepared to transmit and receive to all of its neighbors all at the same time, not just a single neighbor. Okay, but you get very, very good communications. There's no complication here. If I want to communicate to you, I just dump data on the wire that connects us. So in some ways, we're making communications very high bandwidth at the cost of having to spend a lot of hardware on the wires and on the interfaces on those wires. A slightly more elegant approach, perhaps, is a crossbar switch. So imagine the A's were all your processors, and B's were all your memory modules. And this would be a way in which it would be possible for each processor to access a different memory module all simultaneously. So with carefully orchestrated communications, it would be possible for every CPU to talk to every memory system. In the less orchestrated thing, it's possible for you to get everywhere, okay, but you may get some collisions, right? And so this is one of these probabilistic things now, where depending on how you engineer the synchronization and communication protocols, you can sort of make a balance between getting very high throughput through a crossbar, or it basically, everybody trying to access B1, in which case the crossbar really turns out to be a bus, where we have to all line up and communicate one at a time. But in a large system, it's unlikely that everybody will want to get the same memory location at the same time, particularly when there's caches here buffering up most of the transactions. So crossbars are very popular in the so-called small SMP, symmetric multiprocessors that have 2 or 4 cores. They often have a crossbar switch to deal with things like that. Moving up one more time, now we've given up. We've basically said, look, there's too much collision happening here. I'm going to make communications happen like it happens in Manhattan. You get to travel on streets. There's point-to-point communication. There's this notion of I can route a message from here to here. Go east and then north and then east. And there's several paths, so there's possibility of avoiding hot spots in your communication network. The mesh can be regular, or it can be sort of incomplete. And so modern, high-speed networking, the internet that we're used to, is really some sort of mesh, right? Where some of the communication links have very high bandwidth. This is a very organized mesh, something like that you might put into an integrated circuit. The advantage of this mesh is that there's no wires that have to get all the way across the chip, right? So the wires can be very fast. Long wires are inherently slow. We avoid that with sort of this. And in fact, there's really nothing to prevent us from doing 3D interconnects of one sort or another. So these mesh topologies have been very popular as people start thinking about how to hook together, say, 100 or 1,000 processors. How should they communicate with each other? And typically they use meshes like this with the memories and the I/O system connected at the edges of the mesh, and the middle part of the mesh is completely full of processors communicating one to another. It's possible to build networks that have latencies that don't go as in this case, the square root of n, okay, some root of n, which is what these all do. But instead, we use a tree-like mechanism. These are pictures of hypercubes, or more generally a tree, in which case the longest path from one node to another is logarithmic. Okay, we have trouble embedding 4 cubes in 3 space, so these sorts of hypercubes work well up to a certain point, and then either we have to figure out how to invent more dimensions, or we move to a logarithmic mechanism like this. There was a whole interesting set of technologies called fat trees, which they used a tree-like architecture, and they made these links, which are obviously critical for communicating between this half and this half, have considerably more communication bandwidth than those links. So the idea is the trees got fatter as you got to the top, and the idea was to sort of balance out the advantages of the logarithmic latencies with the increased communication capacity you needed at higher levels. And depending on what you're trying to achieve, any of these topologies may in fact be best. So you as architects will have a lot of different choices to make. Okay. So we can go off and talk about the hardware cost, which is associated with the number of links that are active at any given time. and the theoretical latency. You know, how long does it take to communicate a message from one processor to another? And so this is sort of the theorist's view. And just because we occasionally dip into realism, if we take into account, first of all, that some wires are long, like in the fat tree, there was this notion that, you know, all the nodes didn't all fit into a tiny little space. As you put more and more nodes, some of them got farther apart, and some of the wires had to get longer. Okay, and plus the fact that light doesn't travel infinitely fast, we can sort of change this to reflect physical reality. In other words, some of these things where the asymptotic costs seem to be, you know, low, if we put in the fact that nodes have to be physically separate and things like that, we discover that these are the actual sort of lower bounds on the latencies that we get. So remember, keeping, you know, you can have a theoretically nice thing, but when you package it up and, you know, sell it to the masses, you have to keep track. So where is all this going? Well, I think that, as I said earlier, communication at sort of between components on your system, that seems to be serial point-to-point links. You know, networking, that seems to be a strategy that we figured out, and we use very high-speed point-to-point links, increasingly high-speed. The real challenge now is when we have hundreds of communicating processors all in one chip, we start having some more interesting conversations about possible interconnects. So if you go off and become an architect at Intel or some other modern processor company, you'll probably revisit all these conversations, but now talking about things that are an inch across. So, you know, your scale is much smaller than worldwide, but many of the same problems are still there. Okay. Done. Good luck on your quiz tomorrow, and we'll see you next week. New horizons await us.